Okie dokie artichokes, today's lesson is for section 2.4. This is part 2 of the derivatives of trig functions. So yesterday we worked on the limits of trig functions, and now today we are actually going to find the derivatives of trig functions. The other objective we're going to work on today is to find the equation of something called the normal line that's through a point on the graph of a function. Now, off to the side, you can see in this box all of the derivatives of your trig functions. Now, you will have to memorize these. So the notation here indicates that the derivative of the sine of x is cosine of x. The derivative of the cosine of x is the opposite of sine of x. And as you just kind of read through, you can kind of see some symmetry going on here. All of the derivatives of the co-functions, so cosecant, cotangent, and cosine, these all have derivatives that are negative. And if you look at the others, sine, tangent, and secant, all of these are positive over here. Now there's more symmetry going on here. If you look at the derivative of tangent of x, which is secant squared x, you'll see that it's similar to the derivative of cotangent x, because here it's of course negative, but it's cosecant squared x. And then if we compare the derivative of secant x, we have secant x tan x, which is over here. The derivative of cosecant x is cosecant x cotangent x. So a lot of symmetry going on here. So the memorization isn't that hard if you kind of make sense of some of those little nuances. All right, now we are actually going to prove some of these derivatives, not every single one of them, but we are going to prove 4 of them. We're going to start with the first proof here. We want to show that the derivative of sine of x is cosine of x. So what we're going to do is start with the definition of the derivative. So if we start with the limit as h approaches 0 of the sine of x plus h minus sine of x over h, we can't directly evaluate this because if we plug in 0 here, we end up with 0 divided by 0. So we have to do some algebraic manipulation here. So I think this proof is pretty cool because it actually relies on some of the skills you learned in a couple of chapters ago. If you look at the sine of x plus h, this is something that we can use the angle addition formula for. So if we use that identity, we have the limit as h approaches 0 of the sine of x times the cosine of h plus the cosine of x times the sine of h minus then sine of x. And all of this is over h. Now we can do a little bit of rearranging here because we have this sine of x term and this negative sine x term over here. I'm going to factor out the sine of x. So let's rewrite the numerator here as the sine of x times cosine of h minus 1. And then plus cosine x sine h all over h. All right, so now I'm going to rewrite it one more time, just a little bit more conveniently. We're going to write this over again, the limit as h approaches 0. We'll separate the sine of x from the cosine of h minus 1 over h, plus we'll separate again the sine of h over h. So we're still dealing with the exact same expression here, just rewritten in a form that we're able to evaluate the limit of. All right, so now let's go ahead and try to evaluate this limit. Now I know the limit as h approaches 0 of this expression here, that's something we just proved yesterday, that's equal to 0. And the limit as h approaches 0 of the sine of h over h, that is equal to 1. So just by evaluating here, a lot of the terms are going to drop out. We have the sine of x times 0 plus cosine of x times 1. So obviously that is 0. We end up with the cosine of x. So we've just proven that the derivative of sine of x is equal to cosine of x. So our next proof, we want to show that the derivative of cosine x is equal to negative sine x, and we'll use the same strategy. We're going to start with the definition of the derivative. So we write the limit as h approaches 0 of our difference quotient here, which is going to be the cosine of x plus h minus the cosine of x all over h. And then once again, we have angle addition identities that would apply here, so we can rewrite this as the limit as h approaches 0. Now for the cosine angle addition, remember that's cosine, cosine, change, sine, sine. So we have the cosine of x, cosine of h, minus sine of x, sine of h. And then minus, of course, the cosine x still. All right, maybe now you're catching on here as well in this step. We can rearrange the numerator here and we can factor out a cosine of x. So we have the limit as h approaches 0 of the cosine of x multiplied by the cosine of h minus 1 minus sine of x times the sine of h all over h. And then once again, we're going to try to rearrange this a little bit more conveniently so that we can evaluate the limit. We have the limit as h approaches 0 of the cosine of x times the cosine of h minus 1 over h. and then minus the sine of x multiplied by the sine of h over h. Now if we evaluate the limit here, we can break this up once again using our limit rules. We can take the limit as h approaches 0 of the cosine of h minus 1 over h, which again is just 0, and we can take the limit as h approaches 0 of sine of h over h, which is simply 1. Okay, so let me rewrite this now, I guess off to the side here. Oh, no, let's save some room. Let's write it below. So let me erase. So we can rewrite this limit here as h approaches 0 of cosine of x times 0 minus the sine of x times 1. So obviously this first term will drop. And if you try to evaluate the limit as h approaches 0 of negative sine x, it's just going to give you negative sine x. So we've just shown now that the derivative of the cosine of x, this is equal to negative sine x. All right, in our third proof, we want to show that the derivative of the tangent of x is equal to secant squared x. Now, what we're going to do is rely on our previous two proofs by rewriting the tangent of x. Okay, so dy dx of tangent of x, this is equal to the derivative with respect to x of the sine of x over cosine of x. So I'm just rewriting that, and now that I've turned this into a quotient, I can use the quotient rule while using the derivatives that I've already proven. Okay, so just by the quotient rule here, we'll have ho d high minus high d ho. So the cosine of x multiplied by the derivative of the high, so that's going to be cosine of x one more time. And then minus high, so sine of x, multiply that by the derivative of the low, so that's going to be negative sine of x, all over ho ho, so the low times itself. So just by simplifying, we now have cosine squared x plus sine squared x all over cosine squared x. Now in the numerator, cosine squared x plus sine squared x, this is a very nice identity. That's just equal to 1. So I have 1 over cosine squared x. Well, cosine squared x we know is equal to secant squared x. So we've just shown now that the derivative of the tangent of x, that is equal to secant squared x. Pretty sweet, huh? All right, we have one more proof that we're going to work through. We're going to show that the derivative of the secant of x is equal to secant x times tangent of x. Now, the other two remaining trig functions, I believe you're asked to prove those derivatives on your own in your homework, so we'll just work on this one, and you can kind of steal the strategies that we used on the previous proofs to help you with your homework, okay? So what we're going to do is we're going to start just like we did with the tangent of x. We're going to rewrite the secant of x. We'll write that as 1 over the cosine of x. Okay, so at this point, we've just created a quotient. Now, this quotient is particularly special because it is actually a reciprocal. Now, we can use either the quotient rule, okay, so you could use the quotient rule in this proof, and it certainly wouldn't be wrong at all, but we're going to take a little bit of a shortcut. We're going to use the reciprocal rule. Remember, the reciprocal rule is a direct result from the quotient rule, and for the reciprocal rule, let's use 1 over x. If we wanted to find the derivative of 1 over x, we take the opposite of the derivative of the bottom, which is 1, and then we take the bottom and we square it. So we get negative 1x squared would be the derivative of 1 over x. So if we apply that same idea here, okay, the derivative is going to be the opposite of, in the numerator, we take the derivative of the denominator, so that becomes negative sine of x, because we know the derivative of cosine x is negative sine x. And then in the denominator, we have cosine x squared. So just by simplifying and rewriting this, we now have positive sine of x over cosine x multiplied by 1 over the cosine of x. So this is still the same exact expression here. Now, as you can see, we just turn that into the tangent of x times the secant of x, which is what we were wanting to prove. We want to show that the derivative of the secant of x is equal to secant x times the tangent of x. All right, so let's now work through some examples where we're going to find the derivative of functions. Now, each of these functions have some sort of trig function in them. So our first example is a function defined as the sine of x over x. Now, I'll have students who right away say that the derivative here is equal to 1. And the reason why they think incorrectly that this is equal to 1 is because they're using that limit theorem that we just learned yesterday, the limit as x approaches 0 of the sine of x over x. This is definitely equal to 1, but the derivative here is not equal to 1, and that's because here we have a quotient, okay? So we're going to have to use the quotient rule. So by the quotient rule, if we found the derivative here, f prime is going to be ho, so x, times d high. So the derivative of the high function here is I'm sorry, not negative. It's just cosine of x, and then minus high, so sine of x, times d ho, which is simply 1, all over ho, so x squared. So we have the derivative here is equal to x times the cosine of x minus the sine of x all over x squared. We can't do any factoring here. Nothing will cancel. Don't try to factor out an x from the sine of x. It's not equal to x times sin, which I've seen students do before, so don't do that. This is as simplified as that particular derivative function gets. Now, in example 2, this is another one of those functions that kind of trips up students when you're asked to find the derivative. They think, okay, the sine of x, that derivative is going to be cosine x, so here f prime is going to have to be cosine of 2x. But this is actually wrong, okay? In order for us to find the derivative here, right now, we don't have skills. We're going to learn how to do this a little bit quicker in another lesson. But right now, what we have to do is rewrite this using a double angle identity. So we know that the sine of 2x, our function here, can be rewritten as 2 sine x cosine x. Okay, so this is just using our double angle identity. Now, if we want to find the derivative of this function, we can treat this as a product and just use the product rule. So I'm going to do something kind of weird at first. I'm going to consider this its own function too, and then this a different function, okay? So just to illustrate here that we can actually pull the 2 out and then consider only the derivative of the sine of x times the cosine of x, all right? So the reason why we can kind of separate that is if we looked at this as 2 different functions, we would take the derivative of or we would leave the first alone, right? And then we take the derivative of the second, so whatever that is, okay? Then we would add to that the derivative of the first, which is 0 times the second, and clearly this term here is going to drop out. So what we're going to work on only is taking 2 times the derivative of this guy. So that's what we're going to work on here, okay? So that's just an explanation of why I'm going to rewrite this line as 2 times whatever our derivative is here. So I'm working on a product, which means I can use the product rule. So by the product rule, we're going to take the first factor, which is sine of x, and multiply that by the derivative of the second factor. Now the derivative of cosine is negative sine x. And then we'll add to that the second, which is just cosine of x, and multiply that by the derivative of the first factor. So that's cosine of x again. Now, if I just simplify, I have 2 times negative sine squared x plus cosine squared x. And if I rewrite that as cosine squared x first minus sine squared x, it might be a little bit easier for you guys to identify. Well, this is another identity. Okay, this is the cosine of 2x. So we have the derivative of the sine of 2x is 2 cosine 2x. Okay, now example 3 is an example where it pays to kind of simplify this before you try to just jump right into maybe the product rule here. Let's try to rewrite this. The secant of theta is 1 over the cosine of theta, and cotangent of theta is cosine theta over sine theta. Now I can cross cancel here, and I've simplified this now to 1 over sine theta. So if I find the derivative here, I can apply the reciprocal rule. So remember, the reciprocal rule says you're going to take the opposite of, take the derivative of the denominator, so that's cosine theta, and stick it in the numerator here. Then you take the denominator and you just square it, so sine squared theta. Now if I rewrite this, this is negative cosine theta over sine theta times 1 over sine theta, and that is equivalent to the negative cotangent theta times cosecant theta. Now, if you recognize this, just from the note sheet above, this is the derivative of the cosecant of theta. The derivative, so dy, or sorry, yeah, I guess it's dy d theta. So dy d theta of the cosecant of theta, that's equal to negative cotangent theta cosecant theta. So you could have avoided all of this work here if you recognized right here that this is the cosecant of theta. So it's definitely in your best interest to memorize all the derivatives so you can kind of take some shortcuts, okay? All right, now I think example 4 is the bomb. It's just a cool question because it weaves in so many different skills that you've accumulated over the course of pre-calculus and so far up to this point in your calc class. So we're supposed to find the x-coordinates of all points, so notice that there are multiple points, on the graph of this function here at which your tangent will be horizontal. So the calc side of us says if you're looking for the tangent to be horizontal, that means you're going to set your derivative equal to 0. That means your slope is 0, right? So if we find the derivative here, It's not too difficult in this question. We can take the derivative of each part. The derivative of 2x is 2. And then similar to what we just did with the product of 2 times the cosine of x times sine of x, remember we can just separate this 4 here. So if I pull out that negative 4 and I look at just the derivative of cosine of x, that's negative sine x. So the derivative here of our function is 2 plus 4 times the sine of x. So if our tangent is horizontal, then that means the slope of the tangent is 0, which means your derivative, which represents the slope, has to equal 0 as well. So we're basically solving the equation 2 plus 4 times the sine of x equals 0. Now, let's think about this graphically real quick. Not that we have to do it this way, but if we thought of it graphically, we have a sine function here. If we were to graph this as an amplitude of 4, and it's shifted up 2 units, so this would be 6 right here, 6, and then that would be 2, and this would be negative 2 here. And we'd be looking for all the points on the graph. That's why it says find all x values, all the points. We'd be looking for where it intersects the line y equals 0. Now, obviously, you don't have to do this graphically, because if you come back over here and you just solve for the sine of x, we have the sine of x equals negative 1/2. So if we think about where the sine of x is equal to negative 1/2 on our unit circle, that's going to occur at the pi over 6 families, and it's going to be in the 3rd or 4th quadrant. So that's going to be 7 pi over 6, or at 11 pi over 6. So all of the x coordinates for the points on the graph of 2x minus 4 times the cosine of x, where your tangent will be horizontal, all of those x coordinates should be in the form 7 pi over 6 plus the multiples of 2 pi, and 11 pi over 6. Plus multiples of 2 pi. So these are all of the different x values for which you have a horizontal tangent on the graph of this particular function. Okay, our last problem of the lesson is technically a skill that you have already. We've done problems similar to this, but we've never done one with a trig function, obviously. And we've also never found the normal line before. So this is a new vocabulary term that I need to explain. So in the diagram to the right here, we've got some function in blue, okay, and a point that lies on the function. Let's call it P. Now, we've got the tangent line drawn in. So this is the line that is tangent to the graph at point P. And then the normal line intersects that tangent line. The way it intersects, though, is special. It is perpendicular to the tangent line. So a normal line is a line that is perpendicular to a tangent at a specific point P on the graph of a function. So if this question is just finding the equation of a tangent line at a specific point on the graph of a function, you've done this plenty of times before. Now it just involves, a trig function, so it looks harder, but it's really no different of a process. You have to find the derivative, so we have to work on finding f prime here. Now f prime is going to be the derivative of secant x plus the derivative of tangent x. So derivative of secant x, that's tan x times the secant of x. So that's something you need to have memorized. And then the tangent of x, that derivative is going to be secant squared x. Now, typically, once we find that derivative, what we do is we evaluate the derivative at the x value so that we can find the particular slope at that particular coordinate. So we're going to evaluate f prime of pi over 4. So when we take the tangent of pi over 4, we just plug it in everywhere, and the secant of pi over 4, and we add to that the secant of pi over 4 squared, we're just evaluating piece by piece. Now, the tangent of pi over 4, that's just 1. And the secant of pi over 4 is like taking 1 over the cosine of pi over 4. So we're really just evaluating the cosine of pi over 4, which is root 2 over 2, and then we just flip it. Okay, so we get 2 over root 2. Now once we rationalize here, and the only reason why I'm bothering to rationalize is so we don't deal with the radical in the denominator all the time, we end up with just root 2. Okay, so the secant of pi over 4, that's simply root 2. Now here, this is nice because we've already evaluated secant pi over 4. So we're just going to take root 2 and square it. So we have a slope here that is root 2 plus 2. So it looks weird, but this is the slope of your tangent. Now, in order to write the equation of our tangent line, we need to have the slope, which we just found, but we also need to have a point that lies on that tangent line. Well, we should already know, right, that this point here lies both on the graph and on your tangent. So what we have to do is figure out this f of pi over 4, because we don't know the y value. Sometimes they just give it to you, but here we don't know it. So what we'll have to do is find f of pi over 4. So we're evaluating this function over here. So we find the secant of pi over 4 plus the tangent of pi over 4. Okay, and that's easy for us. We just evaluated that. That's going to be root 2 plus 1. So this represents the y value, okay, of a point that lies on both the graph and your tangent line. So we have pi over 4 comma root 2 plus 1. So when we try to write the equation of the tangent, so the tangent line here, we're going to use this coordinate. So we have y minus, and I'm going to put this in parentheses, root 2 plus 1. Or you could just distribute the negative here, and you could rewrite that as root 2 minus 1. That would be fine as well. But I will keep the parentheses. So root 2 plus 1 equals your slope. So our slope isn't a pretty looking number, but it's still a slope right here. And then multiply that by x minus pi over 4. So this is the equation right now of the tangent line. Okay, so now that you've gone through all of that work, finding the equation for the normal line is actually really easy to do. So you already know that the normal line has to go through this point, right? And it's also perpendicular to the tangent. Now, the fact that it's perpendicular to the tangent means you can kind of steal this slope here, and all you have to do is take the opposite reciprocal, because perpendicular lines have opposite reciprocal slopes. So when I write this equation, I'm going to keep that same coordinate. So I have y minus root 2 plus 1. And then when I get to the slope here, I'm just going to rewrite that as the opposite reciprocal. So I take negative 1 over root 2 plus 2. And then I keep x minus pi over 4 the exact same. So this represents the equation for the normal line, while this is the equation for the tangent line. So this problem is finito. All right, folks, that's the end of the lesson. Make sure you guys come into class tomorrow ready to work and ask good questions. Nice job. See you mañana.